How you doing, guys? How's everybody doing today?
Good, how are you?
Let's just admit more people. All right. So some administrative stuff to talk about while people are still joining. Don't forget we have a quiz that opens up today at 3 o'clock. The quiz is on chapter 1.2 and 1.3. Okay, this is in the multivariable book. If we have time today at the end of class, I can maybe answer a question or two on those homework problems. We'll see how we're doing on time. Today we're doing chapter 1.5. It's most likely that we'll get through most of it. Probably we'll just wrap it up on next Wednesday's class, next Wednesday, because remember, there is no school on Monday. That's the April 12th is the date that the provost switched with April 19th. So we used to have April 19th off, and then now we're switching it. So we have off on the 12th, and then we have classes on the 19th. So the 19th and the 21st are classes in the last week. So we only have those two in our very last week. But next week, we have only Wednesday and Thursday. Okay, so we'll wrap up chapter 1.5 next week, Wednesday and Thursday. And I wanted to ask you guys, I think I already know the answer to this, but I wanted to ask to be fair. If you wanted to have a quiz next week on chapters 1.4 and 1.5, you can write that in the chat. You can do it anonymously, or you can tell the whole class. Either way is fine. And you know, we can kind of see how it goes. I'm totally okay with leaving today's quiz as the last quiz of the semester, but if you feel like you want to have another quiz, that's fine. 1.5 is the last bit of material that we're going to cover. That's correct. So we've got excuse me, sorry, we have 1.2 to 1.5 in the multivariable book. We went very quickly through 1.1. It was kind of mostly like, I didn't even give you homework problems for that. It was just kind of, we looked at nomenclature stuff. But we can have a quiz for 1.4, 1.5 if you want. We still have the homework due for that material. So that homework 1.4, 1.5 is still due next week. So next Thursday, which is the 15th, the homework will be due. Okay, so keep that in mind. You'll have the homework. But I know you guys are all interested in having another quiz, right? But I'm good if you guys don't want to do that. Totally fine. If you want to have today's quiz be the last one. You can think about it. You can write it in the chat, or you can send me an email, either way. Like I said, we're going to wrap up 1.5, and then what I'm going to do probably tomorrow is start putting up some old exams, final exams, for you guys to take a look at. These are exams I'm going to put onto the last module, so that on our Canvas page, the last module is the one that it'll say like review materials for final exam, because basically once we wrap up 1.5 next week, I'll answer questions about homework for 1.5 and homework for 1.4 next week. Looks like nobody else wants to have a quiz. That's okay. Then next Wednesday, we'll go over the homework for 1.5 and 1.4. So, you know, take a look at those over the weekend and then come prepared to ask questions about them next Wednesday. Okay, so that we can kind of wrap up our multivariable stuff. And then next week, Wednesday, Thursday, next week, we'll start our final exam review. Okay, and then the following week, the 19th and the 21st, our last 2 days of classes, we'll have a review. If you guys want material, the stuff that we skipped in chapter 3, I'd be happy to cover that as well. I mean, you won't be held accountable for it, but if you want to have that, that's fine. Anyway, for those of you just joining, we were just whether or not to have a quiz next week. It looks like we're going to vote not to have a quiz next week on chapter 1.4, 1.5, which is totally fine with me. But the homeworks for that will be due next week. So make sure that you do those, because you'll need that material for the final exam. Okay. Alrighty. So with that said, let's go ahead and get started. I've got the lecture examples for 1.5. I'll probably scan them in next week, because we in my 9 o'clock class, we still have one more example to do, one more concept to finish up. 1.5 is a pretty important topic. It forms the basis for some pretty interesting things that happen in both linear algebra as well as in kind of 3-dimensional space. So we're going to talk about chapter 1.5 today, which is called on the outside the cross product, which I'll subtitle using the cross product to, give me a sec, to describe or derive an equation for a plane. And this is in R3, okay? So remember when we were talking about vector multiplication, we talked about scalar multiplied by a vector. So that's just like taking 3 and then multiplying it by all the components of a vector. We talked about vector multiplication. We talked about the dot product, right? Where the dot product, I take in 2 vectors and I output a scalar. The cross product, let's talk about what that is. The cross product, our input is 2 vectors. They're both in R3. Okay, so they're both 3-dimensional vectors. And our output is 1 vector, which is in R3. And this vector, which is normal, right, which means don't forget perpendicular or orthogonal at right angles to both of the 2 input vectors. Now remember, how do we check to see if 2 vectors are orthogonal to each other? We use the dot product. If I do vector 1 dot vector 2 and that's equal to 0, that means that the angle between the 2 vectors is 90 degrees or pi over 2, okay, which means that they are perpendicular to each other. So my cross product takes in 2 vectors and it returns another vector. So it's going to look like this. So I'm going to draw, let's draw this out. So I've got vector 1 and I've got vector 2. Okay, so I've got these 2 vectors. We want to say that our 2 input vectors, vectors are not parallel. We'll see as we go along, we're going to talk about the geometry of this too, that the cross product uses the sine of theta. So if the 2 vectors are parallel to each other, my cross product is going to be equal to 0. You don't want to use the cross product necessarily to see if they're parallel to each other because it involves a lot of addition, subtraction, multiplication. It's much more energy consuming than if I just checked scalar multiples of all of my components, okay? But it is something that you can take a look at. So the 2 vectors, input vectors, are not parallel, right? They're going to be intersecting at some particular point. What I'm going to do is I'm going to draw a normal vector coming off of that, right? So I've got, we can think about this as I've got a cross product. And if you guys are familiar from physics, the right-hand rule, this is my right-hand rule, I'm going to go the direction that we're crossing. So if I go V2 cross V1, this is the direction of the normal vector, okay, the vector that's coming as a result of my cross product, okay? Our book talks about it like you can make the V symbol with your 2 fingers, you spread them apart, and then you stick your thumb up, okay? And it's hard to describe this on the camera, but it looks like this. So these are our 2 vectors, okay? These are 2 vectors that intersect each other, and this is the direction of the normal vector. Likewise, if I did V1 cross V2, I'm gonna get the same normal vector, but it points in the other direction. Right, so I can kind of draw this, I'll draw this down like this. This is gonna be minus n. Right, so it's the same normal vector, but it just points in the opposite direction. So if I say V2 cross V1, that's going to equal to my normal vector. Okay, if I do V1 cross V2, that equals minus my normal vector. Okay, so unlike with the dot product, we're ordered in matter because we were adding everything up, we're going to see that there's a subtraction, multiple subtractions that are happening within our cross product. Okay, so order matters when we do this, okay? But the result that we're going to get is the same vector, but just opposite direction. So keep that in mind, okay? So before I go into giving you the formula for the cross product and whatever, I want to take a step back and tell you where does the cross product come from so that the algorithm for figuring out how to do the cross product makes sense to you. Okay, so let's talk about where does the cross, whoops, I can spell cross product come from? There, cross product come from? And it comes from, in linear algebra, it comes from the idea of a matrix, right? If I have a square matrix where my rows are equal to my columns, right? So the number of rows equals to the number of columns, right? I've got a matrix and I want to take what's called a determinant. So in matrix theory, matrices, we talk about M by N, where M is the number of rows and N is the number of columns. Okay, so I'm going to give you, this is going to seem like I'm going off on a tangent, but really it's going to matter for when we want to talk about the cross product. So when we talk about matrices, the position within the matrix is important. So I'm just going to describe a 3 by 3 matrix. So 3 rows and 3 columns. So this is whatever it is, some number, right? And you guys remember matrices are representing the coefficients, okay, of terms in a system of equations. Okay, so I strip out their coefficients, I put it in a matrix, I can do stuff with it, and then it tells me about how does that system of equations interact, and all sorts of other stuff, which, you know, if you take linear algebra, which I think you're required to do, then you'll get a lot more of this. Anyway, so my first, we say this is our first row, first column. So I'm going to put a subscript. That looks like 11, but it really means first row, first column. So we say 1, 1. This position here is my first row, second column. This is my first row, third column. This looks like 11, 12, 13, but it's not. It's first row, first column, first row, second column, first row, third column. And I'm going to go down. So I'm going to go, this is my second row, first column. Second row, second column, second row, third column. This is my third row, first column, third row, second column, and third row, third column. So this is a 3 by 3 matrix, right? 3 rows and 3 columns, so square. Now we'll do a 2 by 2 matrix, and the reason we're going to do that will become apparent in a minute. So my 2 by 2 matrix is going to be, got my first row, first column, my first row, second column, my second row, first column, and my second row, second column. So this is a 2 by 2 matrix, okay? When we go to figure out, there's a process called the determinant. Now in linear algebra, the determinant gets used to describe the system of equations, okay? And it's gonna allow us to do certain things or not other things, okay? But the process of finding the determinant on a matrix is the basis for how we're gonna find the cross product. So if I do my determinant, right, everything, the whole goal is to reduce everything down to a 2 by 2. So I can do a determinant on any square matrix, like 10 by 10, 100 by 100. There's whole algorithms, but ultimately you're reducing it down to a 2 by 2 matrix. And what happens is, I'm going to say, it looks like absolute value. It looks like absolute value, but it's not. It's the symbol for taking the determinant. It's going to be our symbol for doing the cross product too. So when I go to do the determinant, I'm going to multiply across. I'm going to multiply across. This is our cross product, right? And then I'm going to subtract those. So I'm going to go this diagonal first. So A11 times A22 minus this product here, A21 times A12. Okay, this is my determinant of a 2 by 2 matrix. This is a number. It's just a number. Okay, in our cross product, when we do it, you're going to see we're going to get a vector. You'll see why and how. Okay, so this is a 2 by 2 determinant. If I do a 2 by 2, a determinant of a 3 by 3, watch what's going to happen. A11. Actually, you know what? Let me do this. I'm going to do the determinant on the other side so I have room to work. You guys will have this here before I turn the page. Okay, I'm gonna start writing this on my other page here so I've got room to work. Okay, so if we do a determinant with a 3 by 3 matrix, it's gonna look like this. So I'll put the numbers A11, my first row, first column, first row, second column, first row, third column, second row, first column, second row, second column, second row, third column, third row, first column, third row, second column, third row, third column. It helps to say it in your mind. Okay, saying it in your mind helps you keep track of where things are. So when we take the determinant in linear algebra, when you go to do this, you'll find that you can use any row or any column. They call it a column 1 expansion or row 2 expansion when we calculate the determinant. But when I'm going to keep it as just a first row expansion, because that's how we're going to do the cross product. So just so you know, when you take linear algebra, you can do with any row or any column, not diagonals, but rows or columns, and you'll get the same answer. But for us, we're going to just look at just the first row expansion. So what happens is I take these become the coefficients, and I'm going to reduce this down to a coefficient times a 2 by 2 matrix. Watch what happens. This becomes a coefficient. So A11 times, this is my first row, first column. I ignore those terms and I build up a mini matrix of what's left over. Okay, there's this is minus A12. There's a reason why it's minus. It's beyond the scope of our class. I'll tell you if you want to know, but just know that it's a minus. We're going to do the same thing. This is first row, second column. I ignore those terms and I build up a mini matrix of what's left over. A31, A23, A33. And then plus my last term, A13 times. First row, third column, I ignore those terms and I build up a mini matrix of what's left over. Okay, now if we were in linear algebra and dealing with a much larger matrix than 3 by 3, we would have nested multiplications until we got down to a 2 by 2. All right, but for us, we're just dealing with, ultimately when we do the cross product, it's a 3 by 3. Okay, so now I'm going to do my cross multiplication, my cross product, cross, my cross, and my cross. So what's going to happen is this. I say this is A11 times A22 times A33 minus, right, I subtract out this product, A32 minus A12 times, I do this cross, A21, A33 minus A31, A23 plus A13 times A21, A32, I'm running out of space, minus A31, A22. And when we do this with our determinant, we're going to get a number. Okay, we're just going to multiply everything out, add it up, and whatever. So let me show you our first example on lecture examples. This is actually calculating a determinant on a 3 by 3 matrix, just so you can see, you know, the process by which we're doing this, because I want you to understand the process instead of memorizing all the numbers and where do I plug the numbers in. Okay, you want to memorize and understand the process by which you're doing stuff, not just the subscripts. All right, example 1, we're going to calculate the determinant. So we're going to, like I said, we're going to focus on what we call the first row expansion. So I'm going to say this is equal to 2 times first row, first column. I ignore that and I build up a mini matrix, 0, 1, 4, 6, minus 3 times first row, second column. I ignore those. Plus 5 times first row, third column. I ignore those and I build up what's left over. Okay, and now we're gonna multiply across. You have to watch out for your negatives, right? Especially if we're subtracting. We'll write it all down so you can see. So this becomes 2 times 0 times 6 minus 1 times 4 minus 3 times, this is minus 1 times 6 minus 7 times 4 plus 5 times minus 1 times 1 minus 7 times 0. When you do it, you don't have to write out the 0 times, although it can help you, especially here. Remember, this is a minus. Okay, so this is going to be minus 4. Minus 6 minus 28 is minus 34. Yep, minus 34. This is minus 1 minus 0, so this is minus 1. Okay, so now what do we have? We've got basically 2 times a minus 4 minus 3 times minus 34. So watch your negatives. Minus times minus, it's going to make this an addition, right? Plus 5 times minus 1. I'm going to add everything up, and in the end, I got my determinant was equal to 89. The determinant's a number, okay? And so it's going to tell us something about that system of equations. We're going to use this process to help us figure out how do we do the cross product anyway. Let you guys finish writing that, and then we'll start talking about cross product. Okay. All right. So this is where our cross product, the process, comes from. Okay. So it's based on our determinant. So now what happens is this. Let's talk about, I've got two vectors. I'll call it V, which is going to give me V1, V2, V3. And I've got W, my components W1, W2, W3. Okay. Now you can imagine if I want to put V and W into a matrix, I'm going to get, this is 3 elements, and I'm not going to get a 3 by 3 matrix. Okay. So when I go to think about V cross W, and I also want my answer to be in the form of a vector, I must use my unit basis vectors I, J, and K. So remember, I is equal to 1, 0, 0, J is equal to 0, 1, 0, K is equal to 0, 0, 1. These form like this represents our X position, J represents our Y position, K represents 1 unit in our Z direction, Z position. So V cross W, order is important. If it's V cross W, V comes first. So I'm going to go V1, V2, V3. Cross W, W1, W2, W3. Okay. Now it's going to look just like we did with the determinant, only instead of numbers out front, we're going to have I, J, K. Okay, so let's go ahead and write this out. So I, first row, first column, I ignore those terms and I build up a mini matrix of what's left over. Minus J, remember it's minus J. First row, second column, V1, W1, V3, W3, plus K. First row, third column, V1, V2, W1, W2. So first row, third column, I ignore those and I use what's left over to build up a mini matrix. So now we're going to do multiplying. This is our cross product here, here. So watch what happens. I'm going to get I times V2, W3 minus W2, V3 minus J, V1, W3 minus W1, V3 plus K, V1, W2 minus W1, V2. Okay, remember, these form the components for our resultant vector. This is equal to a vector. This is the normal vector to both V and W. Okay, remember, I can add up a vector as a sum of my I, J, and K. But really, if you want to write this as a vector, you would say this is my X component, V2, W3 minus W2, V3. Please don't memorize this, just memorize the process. We're gonna do examples so you see the numbers. I'm just putting this down so you can see they form that. This negative you have to watch out for because you're going to negate what's in here. So this is going to become minus V1, W3 plus W1, V3. And then here plus V1, W2, W1, V2, right? So this is our normal vector, okay? I just did it as a sum of my basis vectors, or I can write it in vector form. We're gonna use this right here when we do our examples, okay? So like I said, please don't memorize this. It's just too many letters and numbers to try to memorize. Remember the process, how you're setting it up. Okay, we're going to do examples, so you'll see that process over and over again. Okay, so you guys finish writing that, and then we're going to take a look at our examples 2 and 3. Okay. You guys all set writing it? Okay. Alrighty. So example 2, we want to calculate the cross product of these two vectors here. Now they're both 3-dimensional vectors. First off, they have to have the same dimension and they need to be in 3 dimensions. So my cross product is going to be, I'm going to set up I, J, K as my first row. This one comes first, 3, 1, 2. This one comes second, minus 5, 0, 4. Okay, I'm taking the cross product. So I'm going to write this out. I times first row, first column, I ignore those. 1, 0, 2, 4. Minus j. First row, second column, I ignore those and I use what's left over. Plus k. First row, third column, I ignore those and I use what's left over. 3, 1, minus 5, 0. Okay. Let's do our cross multiplication, our cross products. Okay, let's see what we get. I times 1 times 4 minus 0 times 2 minus j. So 3 times 4 minus, watch out, minus 5 times 2 plus k. 3 times 0 minus, watch out, minus 5 times 1. Watch out for your minus minus because you want to keep track of your signs. So this is 4 minus 0. This is 12 minus a minus 10, so 12 plus 10. This is 0 minus a minus 5. Okay, so be careful. Maybe you take notes. It's only going to take you a second or two to write these things down. It's going to save you from making a mistake later. So 4 minus j, this is 22, plus k times 5, which I'm going to write as a vector 4 minus 22, 5. Notice how I took the minus into the 22. And this is our n, our normal vector to both of these. You shouldn't take my word for it that it's normal. Example 3 says, check to make sure that this normal vector is really normal to both of these. Well, what's our method for checking to see if something's perpendicular? Is our dot product. We expect our dot product to equal to 0 if the two vectors are perpendicular to each other. Okay, so let's try it. So I'll take this first one. Now with the dot product, the order doesn't matter. Okay, so my dot product, so 3 times 4 plus 1 times a minus 22 plus 2 times 5. So this is 12 minus 22 plus 10. Positive 22 minus 22 is equal to 0. Check. These two are perpendicular. That's number 1. Number 2, I'll take the other one. So I'm going to go minus 5, 0, 4 dot product with my resultant vector. What do we get? So I'm going to get minus 5 times 4 plus 0 times minus 22 plus 4 times 5. You can see what's going to happen, right? So this is minus 20 plus 0 plus positive 20. So 20 plus a minus 20 is equal to 0. Check. These two are perpendicular. Okay. So we just did a quick check. Okay. All right. Let's talk about geometry of the cross product. All right. We talked about the geometry of the dot product, but now we're going to talk about the geometry of the cross product. Okay, so there's a parallelogram rule with this one too. Rule. So let's draw it out. So I've got these two vectors. So here's W and here's V, right? And my parallelogram rule says, and I'll do this in a different color. So my parallelogram rule says, I can make a vector. This is my V, and then here's my W, right? So I can form a parallelogram out of them, right? By making this is parallel here. Now, here's my parallelogram. Now I can drop this down. This is the height of my parallelogram, okay? W and V are separated by an angle theta, okay? So if I want to start thinking about how do I calculate the height given W, V, and theta, I'm going to go back to my right angled trig, which is SOHCAHTOA. So I'll say the sine of theta is opposite over hypotenuse. So that's the height divided by, I can't just put it as a vector, it has to be the magnitude, because the magnitude is the length of that side. Okay, so it's that. So if I want to solve for the height, I just multiply magnitude of W times the sine of theta. So our cross product is based on the sine of our angle between the two vectors. Remember, our dot product is based on the cosine sine here. Now the area of the parallelogram is equal to base times height. Okay, we just calculated out the height. The base is equal to the magnitude of my V vector. So my area is equal to the base times the height. Okay, which incidentally is equal to the magnitude of V cross W. The magnitude of my cross product is equal to the area of the parallelogram, which is also equal to magnitude of V, magnitude of W times the sine of theta. In this way, we can use it to figure out what's the angle between these two. Although dot product is easier, it's cheaper, right, to figure out what's the angle between something. Okay, this cross product takes a lot of calculations, right? So in terms of computational efficiency, the angle between two vectors is more computationally efficient to use the dot product, but we can do it here too. Now, you can imagine, right, let's draw this. I'm gonna go right through my word height here. I've got a triangle. We call this the triangle is spanned by my two vectors, right? Triangle spanned by W and V, right? So I've got this W, here's my V, and then I can make a triangle, right? So this is my triangle that's spanned by these two vectors here, right? And so we had theta, and then here was our height, right? So now if I want the area of the triangle, that's equal to half the area of my parallelogram. Okay, so the area of the triangle is equal to half of our cross product, magnitude of our cross product. Okay, now it doesn't matter if I go V cross W or W cross V, because we're taking the magnitude. Okay, so don't worry if you did it the other way. It's the same when you take the magnitude. Okay, so this is area of our triangle. Okay. So what I'm going to do is I'm going to take this stuff here. I'm going to go back to example 2 and 3. I'm going to take that cross product and I'm going to figure out the area of the parallelogram. And we're going to see what it looks like. We weren't asked to do it, but I'm going to do it. I'll do it in green so we can see that it wasn't asked. We're just doing it anyway. So let's do this. So this is the area of parallelogram is equal to the magnitude of the cross product, right? Which is the magnitude of what we're calling n, which is that 312 cross minus 504. We didn't give them names. I'm just putting the numbers in. So that means I'm going to go magnitude. Says I take each component, I square it, and I sum them up, and then I square root it. So when you get these squares, I didn't bother writing down squares. I just summed it up. 525. You can leave it like this. This is fine, or you can simplify. Keep it in simple radical form. 5 radical 21. So this is the area of the parallelogram spanned by these two vectors. Okay. We weren't asked to do it. We're just filling it in anyway. Okay. Leave it in simple radical form. Unless you're told specifically give a decimal out to like the thousands place or whatever, just leave it in radical form. All right, so just a note too about the cross product. We kind of mentioned this on our first page, but let me just make sure I've got it out there. V cross W is equal to minus W cross V. So it's anti-commutative, right? At the negative. But what this means is we have the same vector, just opposite direction. Right, if you think about, right, when I do this, we're going to get the normal vector, And when we do this, we're going to get a minus the normal vector. It's the same thing, right? It's just if we took the magnitude, it's the same magnitude 1. And if you think about it as a line, you know, it's the same vector. Okay, one just points in one direction than the other. Okay. Also, let's talk about if I have a scalar A and B, and if I have vectors P, Q, and R. Say, for example, we were doing a couple different things. So I said P cross A times Q plus B times R. What am I going to get? Watch the order. So the P goes in here. So I'm going to go A times P cross Q. The order matters, right? Plus B times P cross R, right? If this was going to be Q cross P and R cross P, then I would factor it out and I'd do cross P over here. So the order matters. Remember that, especially if we're doing an addition, a linear combination at the end. What you want to be thinking about, why do we care about this? Because if I have this, right, I have 2 cross products, 2 scalar multiplications, and an addition. Here I have 1 cross product, 2 scalar multiplications, and an addition. So this right here is less computationally expensive than this one, because the cross products, you know, they've got like a lot of computations, right? We've got the, you know, multiplications, additions, subtractions, and stuff. So, you know, keep that in mind when you're writing code to do these analyses. Then you want to be thinking about efficiency so that you can do more pieces of code, even though in a shorter amount of time. Even though I know that the computational processing speed is pretty high right now, we still want to optimize our code so we can do more. All right. All right, example 4, let's talk about example 4. Example 4 is really important because we're going to use 3 points to find the equation for a plane. Okay, I think you may have some homework problems like this too. So you know how when we go to find the equation for a line, we need 2 points, right? Because with 2 points, I can calculate out a displacement vector, and I can use one of those points as my initial point. Now I have a vector equation for a line. If I have 3 points, I can use that to calculate 2 displacement vectors, take their cross product to find the normal, and now I can come up with an implicit equation for my line. For my plane, sorry. So let's do this. So we've got these 3 points, A, B, and C, and they're gonna, all these 3 points are on the same plane. So I'm not gonna plot this in the coordinate grid. I'm gonna, because it gets kind of messy, but here's our plane. It's an infinite plane, but obviously I'm drawing it as a finite shape. Here's my A point, my B point, and my C point. I'm not drawing this to scale, by the way. So now I want to kind of visualize in my mind what I'm trying to do. I need to pick an initial point to calculate out both of those vectors. That the initial point has to be the same for both of those displacement vectors, otherwise my math is going to come out funky. So I'm going to pick just randomly. It doesn't matter which one you choose. Normally you try to choose the one with the most zeros, but I'm going alphabetical here. So I'm going to go from A to B, and I'll call that vector V1. And I'm going to go from A to C, and I'll call that vector V2. Okay, so the first thing that we need is we have to calculate displacement vectors. Okay, so we pick one initial point, and I'm going to say V1 is equal to the vector going from A to B. Remember, displacement vector is terminal point minus initial point. Okay, so that means I'm going to go B minus A. Okay, my terminal point is B, my initial point is A, so I'm going to go like this. B is 2, 1, minus 1, minus my A, 1, 0, 1. So my V1 is equal to 2 minus 1, 1 minus 0, minus 1, minus 1. Okay, that's my V1. Do the same thing for V2. V2, we're going to go from A to C, which means terminal minus initial. So 0, 3, 0, minus 1, 0, 1. Okay, remember they have to have the same initial point here. Okay, so the 0 minus 1, 3 minus 0, 0 minus 1 is equal to V2. Right, now it doesn't matter if I go V2 cross V1, Okay, we're going to go V2 cross V1, and you'll see we're going to get the same answer either way. If I go V1 cross V2, if I say V2 cross V1, right, I'm going to get a vector that's normal to both. I'll call that my n, right? This is the graph, and it gets really busy and messy quickly, but this kind of helps me picture what's happening. So I'll say V2 cross V1. Okay, so this is our cross product I, J, K. So V2 comes first because we're doing V2 cross V1. So -1, 3, -1. V1, 1, 1, -2. So let's go ahead and do our cross products. So I'm going to say I times first row, first column, and I build up 3, 1, -1, -2, minus J, first row, second column, -2, and then plus K, first row, third column, and I use this as a matrix. Okay, and remember, we're going to cross multiply this way. It's not really, cross multiplication is really the terminology for going across an equal sign, but we're doing a crisscross in our product, right? So this is I is -2 times 3 minus a -1 times 1 minus K. This is -1 times -2 minus -1 times 1 plus K. I'm running out of space here. K is 1 times -1 minus 1 times 3. Okay, so let's go ahead and do this. This is I. So this is -6 minus a -1 plus 1. So this becomes -5. Minus J. This is 2 minus plus 1. So that's 3. So that's plus K. -1 minus 3 becomes -4. So then our vector, our normal vector is -5. Don't forget this negative, -3, -4. Okay, this is the same as if I said -n, I could use -n, which would be +5, +3, +4. It's the same vector, it just points in the other direction. We could use it to describe our plane just as easily. I'll use the negatives, and then I'll divide everything by -1 because I know positive numbers are nice to look at, right? All right, so now this is what we would get if we had done is equal to V1 cross V2. No magnitude, sorry. V1 cross V2. All right, so now let's come up with our equation of the plane. Remember, our generic form is A, x minus x naught, B, y minus y naught, C, z minus z naught equals 0, where A, B, C are the components of our normal vector, and x naught, y naught, z naught are a point. I have 3 points to choose from. It doesn't matter. You can choose whichever points you want, okay, to plug into here. You'll get a valid plane equation. I think I chose the point 0, 3, 0 because it was easy. It had a lot of zeros in it. So when I plugged it in, it made the math nice. So let's go ahead and do that. So this is our ABC. I'm going to plug those in. So I'm going to get -5, x minus 0. Now you don't have to write x minus 0. I'm doing it so you can see how I've plugged in those points. Plus a -3, y minus 3. Be careful, this -3 is different than y minus 3. They just happen to have the same number. Minus, would be plus a -4, z minus 0 equals 0. So I'm going to multiply everything through. -5x minus 0 minus 3y. This is plus 9 minus 3 times -3. -4z equals 0. I'm just going to divide everything by -1 just to make it look nice, right? So I'm going to get 5x plus 3y plus 4z minus 9 equals 0. This is correct. This is correct. They're both fine. It's almost like you can think I'm going to add everything to the other side of the equation, right? It's like what we did over here. Okay, so they're both correct. So this is the equation of our plane, the plane that has these 3 points on it. Okay. Now, if I wanted to talk about the area of the triangle, with A, B, C as vertices, right? So let's remember what we did before. So I've got my A, my B, and my C. Like, remember, I didn't plot this in the axis, right? And we found our V1, we found our V2, right? And we found our normal vector, right? This is what we just found here. Okay, so now we want to find the area of the triangle with A, B, C as vertices. Okay, so what I need to do is I have to say area of triangle is equal to 1/2 the magnitude of our cross product. Okay, this, where this comes from, actually comes from this, like a couple 2-page derivation that involves like law of sines, law of cosines, which I'm not going into, but that's kind of like where this comes from here. So why this is true. Anyway, so let's do this. This is going to be 1/2 times the magnitude of our cross product. So this is going to be -5 squared plus a -3 squared plus a -4 squared, summed up, square rooted. Okay, so this is 25 plus 9 plus 16 square rooted times 1/2. This is going to give me 1/2. Sorry, you can't see that. 1/2 times radical 50. And you can leave it like this, totally fine. Or you can simplify it, factoring out, right, 25 times 2. So it's going to be 5 radical 2 over 2. Either way, this is totally fine. If you think you might make a mistake, because we'll have to take off points if you do this part wrong, leave it like that. You guys good so far? I'll let you guys finish writing that, and then we'll go on to our next example. It's probably be the last example we have time for today. Okay. Example 5. Example 5 is an interesting one. So we've got 2 planes. The 2 planes are intersecting each other, and they intersect in a line. And we want to be able to write an equation for that line of intersection. So I've got this plane and this plane. Okay. So let me just draw a picture, and we'll, kind of use that to help us figure it out. So I've got, I've got a plane here, and then I've got another plane cutting out. And then this plane comes down, and then here, there. Okay, so this is plane 1. This is plane 2. I didn't draw this very well. Bear with me here. And this is our line of intersection. Right, these are infinite. These planes go off in infinite directions, right? So this line is infinite, unless we're told to, restrict it. But you draw it finite so we can visualize it. So on our plane, let's remember what we have. So right off the bat, looking at my plane equation, I can extract off the normal to each plane. So this is the coefficients of our x, y, and our z. And my normal for this plane is the coefficient for x, y, and z. So let me just, I'm going to draw this not very, very well, but bear with me here. So I've got my normal to plane 1, normal 1. And I've got my normal to plane 2. Normal 2, there. So getting a little squished. Now, these two, normal 1 is at 90 degrees to plane 1. Normal 2 is at 90 degrees to plane 2. If I find the cross product of these 2 normals, I'm going to get a vector that's perpendicular to both. And that vector will be the vector that's on that line. So let's write this down. If I go N1 cross N2, I'm going to get V, which is the vector that's on the line of intersection. Okay, so to define a line, I need a vector and a point on that line. So we'll first figure out the vector, and then we're going to think about how we can find a point that's shared between the 2 planes, right, which will be the point on that line. So let's first do this part here. So the vector on the line, which is going to require us to do the cross product. So I'm going to say N1 cross N2. Now remember, if I did N2 cross N1, my V would point this way. If I did N1 cross N2, my V points that way. So it doesn't matter what order you go in. I just went this way. So I, J, K, N1, 1, 1, 1, N2, 1, 2, 3. Okay, so let's go ahead and write this out. So this is going to be I times first row, first column, minus J, first row, second column, plus K, first row, third column. Okay, now remember, we're going to cross product. Cross product. Okay, so this gives us I, 1 times 3 minus 1 times 2, minus J, 1 times 3 minus 1 times 1, plus K, 1 times 2 minus 1 times 1. So this is 3 minus 1, this is 3 minus 1, this is 2 minus 1. So our vector becomes 3 minus 1 is, whoops, sorry, 3 minus 2, I thought I made a mistake. So 3 minus 2 is 1. This is minus J, 3 minus 1 is 2, plus K gives us 2 minus 1, which gives us a vector that's 1 minus 2, 1. So this gives us our vector on the line, okay? Now we need a point on the line. On the line, which is shared by both planes. So I need a point that's common between the two planes. So that means that what I'm going to do is I'm going to set x equal to 0 and then solve for y and z. I'll have 2 equations and 2 unknowns. If it doesn't work for some reason, set y equal to 0 and solve for x and z. If that doesn't work, you are guaranteed that if I set z equal to 0 and solve for x and y, I'll get something, okay? Because unless the two planes are parallel to each other, they're gonna intersect, okay, somewhere, all right? And it may be that it's parallel to both axes, but it's gonna intersect the third axis unless they're parallel. If they're parallel, I'm gonna get a 0 for my cross product. All right, so, which will stop us right there. All right, anyway, so let's go ahead and do this. I'm gonna set x equal to 0, which means for my plane 1, I'm gonna get 0 plus y plus z equals minus 1. 0 plus 2y plus 3z equals minus 4. Now what I need to do to combine them, right, I wanna get rid of the y's. So I'm gonna multiply the top equation by minus 2. So I'm going to get minus 2y minus 2z equals positive 2. 2y plus 3z equals minus 4. And I'm just going to add, when I add, the y's cancel. 3z minus 2z gives us 1z. 2 minus 4 gives us a minus 2. So I get z equals minus 2. I'll take this up, plug it back into here, right? And what do I get? I can plug it into here, it doesn't matter. I'm going to get y plus a minus 2 equals a minus 1. Add 2 to both sides. I'm going to get y equals 1. So it works. So I'm going to get the point on the line. This is one that's shared by both planes, is x equals 0, y equals 1, z equals minus 2. All right, I have a vector and I have a point, which means I can write an equation for a line. Our vector equation is x bar equals x naught, which is our point, plus the parameter times our vector. We have all the pieces that we need. We've got our point and we have a vector parallel to that line. It's on the line. We call it parallel to that line. So x bar equals the point 0, 1, minus 2, plus t times 1 minus 2, 1. There's our line equation. Okay. All right. We actually have some time, so I think what I'll do is I'll finish up the chapter with a final concept, okay? And then on next class period we'll go over homework, for 1.4 and 1.5. So please come prepared to talk about that and or also talk about exam problems. So our last concept for 1.5 is what we call a distance between a point off the plane and a point on the plane. It's our shortest distance. Okay, so this is distance between a point off the plane and a point on the plane. So we're looking at our shortest distance. Okay, and it goes like this. So I've got, let's say I have a point, I have a plane here. Okay, my plane I'll write out as ax plus by plus cz plus d equals 0. So I've got my implicit equation for my plane. Okay, so it's my plane equation. And then I've got my normal vector, which is equal to a, b, c, right? My components of x, y, and z, my normal vector. And then I've got some kind of a point, x, y, and z. Okay, so what I want to do is I want to find, like, and I can have some kind of like a particular point. This would be like my x naught, y naught, z naught that we use to create the plane equation. Okay, if I look for this distance here, that's not my shortest distance, right? So if I find any point on the plane, I'm going to be here forever trying to find which one's the shortest. But what I can do is I can figure out a whole process. I can say that my normal vector, I'll call it n, becomes the vector on the line, right? This is a vector that's on this line. We say it's on the line. We say it's parallel to this line, okay? So this is, we're now coming up with, we're writing a line equation. So I'm going to say x bar equals x, y, z, this point here, plus t times, and I'll call it t times normal now. T is our parameter, normal is our vector. Okay, so it's a vector on that line. And what I want to do is I want to find the point of intersection between this line and the plane. Okay, we need to find this. Okay, once I find that, right, this point right here, that point of intersection, I can calculate the distance between those 2 points. Distance between point x, y, z, which is the one off the plane, and point of intersection is our shortest distance. Okay, so we're going to calculate that. So these are the steps that we're going to follow, okay, that we're going to do. So our last example is actually working through that, okay. It's always good to first check to make sure that your point is not on the plane, because otherwise if it's on the plane, it's going to, you're wasting your time. All right, so what's the shortest distance, example 6, what's the shortest distance between the point and our plane? So let's just check to make sure our point 1 minus 4 minus 3 is not on the plane. So what I need to do is I need to plug it in for x, y, and z and see if the equality holds true. That means the point is on the plane. If the equality doesn't work, it means the point's not on the plane. So I'm going to say 2 times 1 minus 3 times a minus 4 plus 6 times a minus 3 equals minus 1. So 2 plus 12 minus 18 equals, I'll put a question mark, minus 1, put a question mark. So 2 plus 12 is 14 minus 18, so minus 4 does not equal to minus 1, so point is not on the plane. So we're good to go. If the point was on the plane, right, it's our shortest distance is 0, so it doesn't make sense. So that's our, kind of like our first check. So now what we need to do is, let's get out our normal vector to the plane. Coefficients of x, y, and z. So 2 minus 3, positive 6. Okay, this becomes a vector on the line containing the point 1, -4, -3. So we say a vector on the line, this is parallel to the line. Parallel to the line. Remember, this is our equation. Okay, so this becomes our normal vector becomes this vector here. So I'm going to write x bar equals this point 1, -4, -3 plus t times our normal vector 2, -3, 6. So that's the line. Okay, now I need to find out the point of intersection between this line and the plane. Right, so what we do, we break our line up into components. X equals 1 plus 2 times t. Y equals -4 minus 3 times t. Z equals -3 plus 6 times t. And I plug that into the plane equation. Right, so 2x minus 3y plus 6z. So it goes 2 times 1 plus 2t minus 3 times my y, -4 minus 3t, plus 6 times -3 plus 6t equals -1. And I solve for t, right? I'll save you guys the algebra, solve for t. We found t, I found t as 3/49. I'm gonna leave it as a fraction, 3/49. So now I'm gonna plug that t in to find the point of intersection. Right, so it's going to be x equals 1 plus 2 times 3/49, which is, I'm going to convert it to a decimal as 1.22. Y equals -4 minus 3 times 3/49, which is approximately equal to -4.183. And z is -3 plus 6 times 3/49. Which is approximately -2.63. So my point of intersection, 1.22 minus 4.183, sorry, that's a 3, minus 2.63. Okay, so now I need to find the distance between my point off the plane and this thing here. So that's our last bit, distance between points. Okay, so we're going to go, our distance equals my x's. So I'm going to say 1 minus 1.22 squared plus -4 minus 4, I'm sorry, minus 4.183 squared plus, I'm going to go my last term, -3 minus 2.63 squared. Add them all up, square root it. Okay, my distance was equal to 0.4305, whatever our units are. Okay, so we're looking at 1 minus 4 minus 3, dropping it down to our plane to this point here, which is -1.22 minus 4.183 minus 2.63. Sorry, you can't see that. And then this distance here is equal to 0.4305. Okay. Anyway, phew, that's chapter 1.5. Please take a look at the homeworks for that and for 1.4, and then come prepared on Wednesday to talk about these homeworks and also to ask questions about the final exams. We'll start the review then too. Don't forget your quiz opens up in about 20 minutes. If you want to take it today, you'll have until 3 o'clock tomorrow to upload your answers, okay? But make sure you start it tomorrow no later than say 2 o'clock, okay, or 2:15. Okay, guys, have a great long weekend. Remember, no classes on Monday. I'll see you later.
Thank you.
Thank you.
All right, take care.
Thank you.
Bye.